This slide shows the increase in size of the turbines. Now we are actually looking at conceptual designs for 20 megawatt turbines, and the diameters of the structures increases, the height of the turbine increases, the penetration depth of the monopile increases, and the swept area of the rotor increases. That's what determines the amount of energy that you can produce. This has been a sea change because as you can now, with a single position, produce 15 megawatts, where 20 years ago, you needed 5 positions to do that. That really changes the economics in a very significant way.
Hello, and welcome to today's webinar on structures in the marine environment. Today, we're going to focus on offshore wind, but I think you'll see that the principles that we cover will apply to a whole range of other structures, which we'll be covering in future webinars and courses going forward. I'm your host, Craig Price, with the International Water Training Institute, and I'm excited to be with you today on behalf of the Australian Water School. Welcome to all of our global attendees. I hope you'll get a lot out of this, whether you're near offshore wind or it looks like a lot of people may not be near it, but still be able to participate in the design, modeling, or other aspects, other elements of offshore wind. Let's welcome today's presenters, Kim and Matt, and Asia as well. If you, Asia will be in the panel in the background answering your questions. Kim and Matt doing our presentations today on offshore wind projects. So if you could introduce yourselves, let us know how long you've been in the business, and if offshore wind is the main structures that you work on, and if you work on any others as well. So give us a little bit of a background about your career, your background, your insights, and let us know, first of all, where you're coming to us from today. So we'll start in the order that we saw in the presentation. First Kim, then Matt, then Asia. Over to you first, Kim.
Great. Thank you for having me. I'm excited to be here. So I'm coming to you live from Jacksonville, Florida, Northeast Florida on the East Coast of the United States. So it's 8 p.m. our time, but I am happy to be here with you all today. I am a principal consultant with Kleinschmidt Associates. I do specialize in regulatory and permitting. And I have an academic background in marine science that finally married up with my career about 8 years ago, and have found offshore wind to be all the things that I've been looking for. So I can talk about it all day, and I look forward to sharing some knowledge, especially about the permanent regulatory and environmental considerations. So thank you for having me.
All right. Appreciate it. Good to have you with us. Matt, over to you.
All right. Thank you, Craig. And thank you, Kim, who invited me to join this. It's a pleasure to be able to speak to all of you. I'm calling you from Boston, Massachusetts. So Kim and I span the north half and the south half of the East Coast of the U.S. Same time for me as it was for her, 8 p.m. My personal involvement with offshore wind actually goes back about 20 years. And it's been off and on because I don't think it's been a steady gig for anybody for 20 years in the U.S. I've covered a whole bunch of different things. I was on the Cape Wind project as the engineering manager back in 2010, 2014 kind of time frame. I joined WSP, which is a very large engineering firm I know has a presence in Australia, as well as all over the world, and built up an offshore wind practice for them in the US. And in 2021, I moved over to Wood Filstead. We are the detailed designers of the offshore wind foundations. And actually the team of WSP and Wood Filstead designed the offshore monopiles that are being installed as we speak for Vineyard Wind, which is the first commercial scale project in the United States. Awesome. So I look forward to sharing what I know with you. I'll tell you everything I know, and it'll only take a minute.
All right, perfect. Okay, now, as I understand it, Asia, you're coming to us somewhere in between all the our couple of U.S. presenters and the rest of the folks here in the background on the Australian Water School. Let us know where you're coming to us from and a little bit about your background.
Thank you, and half a day, and good morning, everyone. I'm Asia. I'm from Guam. It's a U.S. unincorporated territory in the Western Pacific. My background is that I grew up with a father and a fisherman and got into marine biology field via conservation and watershed management. I became a scientific diver through the University of Hawaii at Manoa and Hilo on a scientific diving program in 2003. And I mainly survey harbors and coastal areas, submerged lands that are within the Western Pacific and Hawaii, state of Hawaii. And I've over time received a lot of opportunity to look at permitting and compliance from the territorial federal aspect, as well as the state and federal aspect, and have been getting into asset management, working with design review for environmental compliance with various firms throughout my career, and have now been encouraging onto interconnecting the cultural resource aspect of it. So it's happily becoming full circle, and there's never a dull moment. So
that's for sure. No, I appreciate that. And what you'll see from these slides today, there are many facets to trying to get a successful project implemented when it comes to offshore wind. Again, you'll see some applications to other types of structures as well. We got a little bit of an underwater perspective as well, some divers on with us, and even in the background who are able to answer some of your questions. Some modelers, 3D CFD, I'll show you some examples of those later on. Engineers, planners, environmental biologists. We've got the full gamut covered. Let's have a look at the poll real quick, and then we'll get right into Kim's introduction to offshore wind. So it looks like most are coming to us from commercial consulting, but a very large contingent from government and planning. Now, most people then, even if they are with government and planning or with the commercial industry, looks like they're from the engineering background. So we do want to focus on both environmental and engineering and the planning aspects. Culture and advocacy, that's something that Asia had mentioned as well, is something that's going to be an increasingly important topic as we get into the permitting. Not very many people consider themselves very familiar, and you'll see that a lot of these projects are pilot projects, and I think that will change, and that was what we wanted to get to in our last question. Do you expect renewable energy to exceed fossil fuels in the next 30 years? Yes, most of you do. No, those are definitely in the minority. We were wondering about putting it out to 100 years. Matt, you had some comments on what might happen if we put that out to 100 years and whether we expected renewable energy to go that far. What are your thoughts on that, Matt?
Well, if I won't be here 100 years from now, that's 100% certain. For those who are still here, if we haven't exceeded fossil fuels by then, this is going to be one toasty place.
Yes.
So buy sunscreen stock.
Exactly. So let's have a look at this. We expect this to be an upward trend here in terms of the contribution of wind energy in general, and offshore wind seems to be a bit. It's a no-brainer that that's some of the places on the planet. When you look at the spread of water on our planet, it makes sense that in some places that's where you're going to want to harvest the wind. So with that, let's have an introduction then about offshore wind from Kim. Matt, Asia, and I will back off in the background. We'll turn our cameras off, but we will be there answering your questions that come in through the Q&A line. Make sure you keep those questions coming early. What happens a lot of times is we'll get all the questions right at the end, and then we don't have time to answer them because we're wrapping things up. So I'd encourage you as the attendees to get your questions in early as these slides are showing. And everybody in the background will be there to answer them. And then Kim will go into the background once Matt comes on and answer your questions then. So keep them coming. I can see your screen just fine, Kim. Over to you.
All right, great. Thank you so much. As I said, I appreciate everyone tuning in today. I'm very happy to be here to talk to you about structures in the marine environment, and in particular, my favorite structures in the marine environment, and those are related to offshore wind. So Matt and I are tag teaming this a bit. I'm going to set the stage. If you saw in the poll that there are a number of people that maybe aren't familiar with offshore wind at all. So I'm going to start very high level and talk about what it is, how it works, kind of retrace the steps as to where we are and where we're going. Because my background is regulatory and permitting, I have an obligatory slide for that to discuss, and then I'll jump into some of the marine environmental and social considerations, including some of the cultural resource aspects of this as well. And then I will turn it over to Matt for a little more of a detailed technical engineering discussion about offshore wind. So let's just jump right in. Big picture, offshore wind farms are generally two types. Those are fixed bottom, such as we see here on the slide. So on the left-hand side, we have monopiles. And on the right-hand side, we have jacket structures, and they are, as the name indicates, fixed bottom. So they are adhered to the seafloor. The other type of offshore wind farms that we have, and this is what we call next generation technology because it's really just developing right now, even from a design perspective, are floating offshore wind turbines. So we'll put these together in a slide so you can kind of see them side by side and in the water column. But we have the fixed bottom over on the left with the monopile and then the jackets, and there's variations of jacket structures. There's also a gravity-based structure. But then we have the new technology, which is the floating. And, some conferences we talk about maybe up to 100 different permutations from a design perspective for floating. But kind of the three front runners that are in the space right now are what we call the tension-leg platform, or TLP, the semi-submersible, and then the spar. And so the difference in when you would use a fixed or floating technology is generally related to a water depth. And there may be other parameters that make you choose one way or the other, but for the most part, you're making a decision as to whether to go fixed bottom or floating based on the water depth. And that rule of thumb in the industry right now is about a 50-meter cutoff. So anything less than 50 meters would be shallower water, and you would be looking more at a fixed bottom structure. Anything deeper than 50 meters would put you more into the floating space. And as it's shown there on the graph, these are tethered to the seafloor. So they're not adhered to the seafloor so much as floating and then tethered to the seafloor. So what does an offshore wind farm look like? What are the components? How does it work? We refer to these as wind turbine generators, or WTGs is the acronym that we use quite a bit. So they are obviously offshore in some kind of configuration, why it's called a wind farm. They might be in an array with a specific grid spacing like we have here in the US. They are connected to each other. The WTGs are connected to each other via inter-array cables. And then those get connected to an offshore substation or substations, depending on how large the wind farm is. You may need more than one. Historically, these have been alternating current, so they've been AC substations, but right now market trends show us that these may be going more into the DC range for the offshore substation. Then the power is pulled together and transmitted via a buried export cable. And right now, as shown in this graphic, the predominant use of this offshore wind energy is to come onshore, connect to an onshore substation, and then power a grid or be connected to a grid. Conversations right now that are happening in real time and kind of the next generation of use for offshore wind generation of electricity is for things like alternative fuels such as hydrogen. So Canada right now, their play in offshore wind is looking at offshore wind as the source to generate green hydrogen. So in the future, this graph may look different where there's alternatives as to where that power is going. Similarly, for a floating offshore wind farm, same arrangement. You have some kind of spacing array layout of your WTGs. They're connected to each other, connect to an offshore substation, and then that power is brought to where it's intended to be used. So the evolution of the global offshore wind market. The first offshore wind farm was actually established back in 1991 by what is now Ørsted and formerly known as Dong Energy. And those used 3 megawatt WTGs. And I say that because when I mention here in just a second where we are now with the industry, it's kind of astronomical and it's still potentially increasing. The technology is evolving at a very rapid pace. So that was 1991. We jump forward in the span between 2010 and 2020 is really when the market started to take off, particularly in Germany and the Netherlands and in the UK. There was about a 10-fold increase in that decade. And then now we're looking at market trends are showing us another 10-fold increase by 2035. So 2021, 2 years ago, in and of itself was a record year for deployment, particularly because China came online at a very big scale with 14 gigawatts. Anecdotally, China also just last month announced the use of a 16 megawatt WTG. So you can see where we have progressed. Still, at this point, most wind farms under development, so not necessarily even operational, but under development, are more in the 8 to 14 megawatt range. But China has now come out already with a 16 megawatt machine. Globally, we're looking at about 60 gigawatts of offshore wind, and the vast majority of those are fixed bottom. But truly, the next territory that we will be looking at in terms of offshore wind projects globally will be in that floating space. Just to give a nod to Australia, for those of you that are here for the Australian Water School for helping put this on or putting this on. You are, it sounds like at the very beginning stages, and maybe some folks even on the call might know this better than me, but the federal government has declared wind energy zones, and there's at least one project, the Star of the South, that is in the news and is looking like the front runner for offshore wind going forward in Australia. So regulatory and permitting, it's very hard to summarize at a global scale, but I will at least give it a nod because any conversation that is had anywhere globally on a podcast, at a conference, in an article, will always lament that permitting is the biggest hurdle. It's at least the first hurdle, if not the biggest hurdle. It's the most time consuming. So, and I'm not, that's neither here nor there. Suffice it to say that countries either should or have or will develop some kind of regulatory framework. There will likely be tiered levels of approval, so maybe starting at that federal level and then tiering down to whatever the lowest level of permitting or regulatory process is appropriate in that individual jurisdiction. The point, though, is the sequencing of these regulatory processes. So if you have a box, you have a flow chart, each individual box may be the same from country to country, but the order of that process can vary, and it does matter. And I say that because all of the developers that came over from Europe and the UK to start in the US had a very surprise awakening in terms of how the US process is different from the processes that they had already been through, really related to risk, uncertainty, and when capital funds are expected to be expended. Due diligence would have you do assessing environmental and social and socioeconomic impacts from this. Of course, we're talking about offshore wind as a renewable energy source to help fight climate change, to help reduce our reliance on fossil fuels, but there are trade-offs. So we need to make sure that we're discussing what those trade-offs are, what the environmental and socioeconomic impacts of building and operating this wind farm is. At the same time, we need to consider the alternatives to reduce those impacts. And if not, then the mitigation, if necessary, to offset some of those impacts. Here is just like I said, it can be a roadmap. In the US, this is our roadmap. We start with a polygon in the ocean and then whittle our way through a series of steps with a number of participants, including a variety of federal agencies, offshore wind developers, stakeholders, folks such as Matt and myself that are the consultants in this space trying to help the project get through this roadmap until ultimately we've got the construction and operation of an offshore wind farm. So what are some of the environmental and social considerations associated with constructing, installing, and operating, and then eventually decommissioning these offshore wind farms? So we start with this kind of mental exercise that says, what are the resources in the particular area, the polygon of the ocean? What are the particular resources that may be impacted? And we look at the offshore as well as the coming onshore and the onshore itself. So there's kind of those three spectrums there. When I say offshore, for us, that means within federal waters, so within federal jurisdiction, generally 3 nautical miles off the coast. And then you've got the kind of coming into shore, near shore, and then you've got potential infrastructure changes and impacts onshore as well. Then we look at, okay, well, what are those impact producing factors? What are the things that are part of this construction and installation or operation of the wind farm that may have impacts? One of the most obvious that's talked about very widely because it is in most of the wind farms under construction or in operation today, and that is pile driving for those monopile structures. So what are the impacts to pile driving? From pile driving, sorry. And then we look at, okay, well, what are the impacts? And then what are the consequences? Are we talking about, decimation of a species type of thing, which sounds very dramatic, but in reality, here in the US, some of the controversies that we have and some of the conversations and the dialogue and the engagement that we have with stakeholders, and this is not a comprehensive list, this is just kind of the bigger picture, but one of our biggest conversations that we have are with the commercial fishing industry. And that is from both an operations standpoint for the industry, so interacting with the vessel traffic that is going out to the wind farm for construction and installation, once the wind farm itself is built and constructed and we have these structures in the marine environment, how does that change, affect, alter the commercial fishing activity? And then also any potential impacts to stocks. The project that I'm working on right now, which is off the coast of Long Island, New York, one of our biggest issues is potential impacts to cod spawning habitat. So it's a potential impacts to the industry itself from a physicality of the structures being there, as well as to what the commercial fishing industry is trying to harvest. On the flip side of that, we've got the protected species aspect. So the Atlantic coast of the U.S., which is right now where most of our efforts are going on for offshore wind, is in the migratory path of the North Atlantic right whale, which is one of the most critically endangered whales in the world. So being cognizant and talking through and understanding what the potential impacts are and how to mitigate those or avoid those impacts to the North Atlantic right whale. We also have visual resources. So you're putting structures in an environment, at least on the east coast of the United States, where there have not been before. Now, our next kind of foray territory in the U.S. at the end of this month, we will be having an auction for areas off the Gulf of Mexico. Putting steel in the water off the Gulf of Mexico is a non-issue because that's been there, is historic, and the tolerance is very different. So even region to region, within a country, you can have different aspects of what impacts may be. We've got the cultural and tribal resources, and the development of the offshore wind space has kind of spawned a subgenre of marine archaeology. And so now we're taking a very active interest in submerged paleo landscapes, which is not really something that had been talked about before because we hadn't been doing disturbing activities this far off the coast that may have those impacts. And then one just a little unique one to put in there for the project that I'm working on are the presence of glauconite sands, which I actually had never heard that word before a few months ago. But you've got this lease area now that the developer has paid to develop, and they go out and do the surveys and have identified that there are some subsurface sands that will result in pile refusal. So while their intention is to go out and pile drive these monopiles as part of the wind farm, the sand won't let them. So this is now kind of a new thing that has come up and that we're trying to figure out how to deal with. And the reason I bring it up is my point earlier about your regulatory framework and the sequence of the steps matters, is because when the developers are committing exorbitant amounts of money, millions up to $1 billion for this polygon in the ocean, they have not done these surveys yet. So we're going out now after the fact and doing the really intense surveys and identifying some of these things that may be problematic or that at least have to have an adjustment to the plan. So I'm going to stop there. As you could tell, I could talk all day, but I will stop and just say that if this is of interest to you, if you'd like to know more about any specific topic that I brought up, Fleischman Associates, we are an environmental engineering and regulatory firm that deals specifically in renewable energy, and I would be happy to take questions or do future training activities. So thank you very much for that.
All right. Thanks, Kim. And as you can see from that previous slide, there are a lot of other facets that could be covered in future webinars. We'd love to have Kim back to present on some other aspects of this technology. One question that came up, we'll turn over to Matt here in a second, but yeah, keep those questions coming in the background. There's been some great ones answered. Matt, you can already get your screen shared here to get ready to kick off. But Kim, just one question that came up on the regulatory side of things. When you go for these permits, how long, are some of these, what's the shortest to the longest? What's the range of time frames? In 50 years, are they going to fall apart and we have to take decommissioning into account? What are the time frames? That's one of the questions that came up in the background. If we could have you address that real quickly.
Sure. So there is with the federal government here in the U.S., there is a lease term. Most of the planning is done for a 25 to 30 year horizon, and I'll let Matt maybe address that if he has thoughts on that as well. But there, as part of the planning, we are also addressing decommissioning. So that is incorporated. So it's construction and installation, operation, and decommissioning for those projects. So right now, what we're factoring in is more in the 25 to 30 year range versus a 50 year range. But this is a very new market. So as the technology evolves, as the processes evolve, as our understanding, knowledge, and awareness evolve, that may evolve as well. So,
Excellent.
yeah.
All right. Well, thanks for that. Asia's answering some questions in the background as well. Kim, a few for you in the background as well. Matt, I'm an engineer, so I'm excited about this part as well. I mean, this is cool stuff to see how this would actually get built. I want to see some of these slides on how big these structures actually are and how you design them. So we'll come back after Matt's presentation and talk a little bit about the combination of getting these things approved, their impacts versus the design considerations. Keep those questions coming in the background. I can see your screen just fine, Matt. Over to you.
Great. Excellent. Thank you very much, Craig. And Kim, thank you for setting the stage here, if you will, on offshore wind. Let me start by just giving folks an idea of the degree of sea change that's occurring in the offshore wind business here over the past 10 to 20 years. This slide shows the increase in size of the turbines. And if you look at, I was working on Cape Wind back in 2014. At that point, I had a 3.5 megawatt turbine with 107 meter rotor diameter. Now we are actually looking at conceptual designs for 20 megawatt turbines. And the diameters of the structures increases, the height of the turbine increases, the penetration depth of the monopile increases, and the swept area of the rotor increases. That's what determines the amount of energy that you can produce. This has been a sea change because as you can now, with a single position, produce 15 megawatts, where 20 years ago, you needed 5 positions to do that. That really changes the economics in a very significant way. So that's part of what is prompting the big growth of the offshore wind business here globally in recent years. So I'll start by talking about monopiles. These are far and away the most common type of foundation for wind turbines, period. And to put that in a little bit of context, there are some floating structures out there, but I'm pretty sure at this point to count the number of floating structures, you don't have to take off your shoes yet. It's still early days and really kind of proving out the various technologies that exist, taking 100 some odd different floating platforms that Kim had talked about and narrowing that down to, the 10 or so that we need. And that's going to be, that will take some time. But it's coming without a doubt because there are many areas out there where we truly need floating because the water depths are so deep. So a monopile basically is just, as you can see in this picture, an enormous tube. The tube is driven into the seafloor. There is another structure that's a tube slightly smaller in diameter, sits on top of the monopile, and that's where you've got access ladders and platforms. That's where the cables come in and out and all that sort of thing. And on top of the transition piece is where the turbine sits. So for scale, there's 2 guys standing in front of that turbine. I'm the short, fat guy on the left. The monopile itself is the first monopile for the Vineyard Wind project, which was designed by my firm, and that is now installed in the waters south of Martha's Vineyard. Monopiles are, and will remain for some time, the most common structure. I'll quibble a little bit, Kim, with the water depths. We're doing monopiles in depths up to 60 meters, especially with the larger turbines. Jackets, you can probably go to 80, possibly 100 meters, and then beyond that is where you need floating. So jackets, it gives you an idea of what the structure looks like. Instead of a single tube penetrating the seafloor, it's multiple tubes penetrating the seafloor. And there are certainly advantages to that because you distribute the load to multiple connection points, soil steel interaction points, if you will. And that is particularly helpful in areas where you've got seismic concerns. So in the APAC region, where you've got earthquakes and off of California, that sort of thing. Jacket structures are being commonly used in APAC as we speak, as that business takes off. But you can see that these are somewhat more complex structures. But just go back to the monopile for a second. It's a big tube. And in that picture, you can see where the plates are rolled and welded together. And you can do that with a fairly automated process. With the jacket structure, it's tubes with a whole bunch of interconnecting braces. And the end connections of all those braces have to be welded by hand. So it's a much more expensive structure to use. You use a jacket when a monopile is no longer feasible. I'll touch on this just briefly. Gravity bases, this is probably the smallest piece of the installed base at the moment. It is quite helpful in some locations for very specific reasons, where penetration, for example, might not simply work, but you've got a firm enough seafloor that you can set a large structure on top of it. These are also very expensive to build. They're basically made out of concrete, which means that there's a whole bunch of steel reinforcing inside the concrete that has to be wired together by somebody with little metal strips in his hand and a pair of wire cutters. So very time consuming, used only in very specific applications. And just providing a little more detail on the three most common types of floating platforms that we're currently looking at. I won't go through all of these, but I'm assuming that we'll distribute these slides afterwards, and you can all see the various pros and cons associated with these different types. And they all have to be, the cables have to be anchored to the seafloor in some means, and these are the three most common types of anchors that we're looking at. And again, each one has its pros and cons, largely depending upon the geotechnical conditions of the soils that you're looking at in the seafloor. So here's where it gets a little more interesting, moving out of the overview and into some more detail. The offshore environment, I'm sure that there's folks out there who know way more about this than I do, but the offshore environment is pretty harsh. And in order to design a structure that's going to last for 25 or 30 years, conceivably even more, in the offshore environment, you have to understand the details of the offshore environment. And this just gives you a sense of all of the different things that we have to take a look at. It's primarily wind speeds and everything associated with the wind conditions, shear, vortex, all that sort of stuff, mid-ocean conditions, waves, currents, and how those things interact, where they light up with the wind, where they don't. And then very importantly, so the mid-ocean conditions and the wind conditions will give you your loading, what the turbine structure has to resist. And then that load is then transferred down into the soil through the steel. And you have to understand exactly what the soil looks like as well. So there's a tremendous amount of data gathering that has to go on as part of these development of these projects. And that fits into the very long timeline that Kim was talking about. And the geotechnical and geophysical data gathering in particular is quite time consuming and frankly, very, very expensive. You're out there with some fairly large vessels that have specialized equipment for long periods of time doing offshore work. And it's very time consuming and very expensive. So just to give a sense of some of the details of the exploration here, we would typically have some sort of buoy that would be able to gather both mid-ocean data. There'd be a current measuring device on there, wave measuring devices on there, as well as what we call a FLIDAR, which is the acronym for floating LiDAR. LiDAR being the device that uses light to determine the velocity of the air based on the speed of the particles that are traveling through the air. And a FLIDAR is simply a LiDAR that's on a floating platform. So we've now evolved to the point where we're doing this with floating buoys, as opposed to not that long ago, we were using fixed structure offshore wind platforms to do all this measurement. We've now moved on to buoys, which does save a lot of time and money. And then there's the vessel out there that you can see a little bit. That's showing somebody doing a geotechnical boring or a cone penetrometer. Those are the two main means of looking at physical penetration of the subsea, of the surface below the sea, to understand exactly what it looks like. Cone penetrometers and borings will give you different types of data, and you'll do a variety of those at various locations throughout the project site. You'll also draw back samples from some of these sites so that you can take the sample to a lab, get its exact characteristics of that particular layer of soil at that depth, and then that will correspond to the data that you get back from the cone penetrometer and the borings. And then the whole thing is tied together with geophysical surveys. So that's the seismic assessment, where we're primarily using seismic data to understand with a high degree of clarity where the different soil layers are, how they change and modulate throughout the site. And then we're able to build that into a 3D ground model, tie it to the geotechnical data, and that produces the set of engineering parameters that we use for the design of the substructure. So then moving into the design phase, we take all of that metocean data and subsea data from the turbine, put that all together, and use that to design the structure and then subsequently to optimize the design of the structure. There's a lot of steel involved in these things. These monopiles can weigh upwards of 2,500 tons each. So if you can save even a few millimeters off of every plate that's in that entire monopile, that adds up to hundreds of tons and thousands of tons of steel across an entire site. Tremendous savings for the project, the developer, and the cost of energy, and also an environmental benefit because you had to produce far less steel in order to get the project functioning. So this is the modeling bit, and I understand that there's quite a number of folks out there who are very interested in modeling. I will give you what I can on this. I'm totally not the expert. I'm primarily a business development guy at this point. They don't let me touch the software, which is probably good. But we have developed in-house through using MATLAB our own tailor-made software for designing both jackets and monopiles for offshore wind turbines. And what we're able to do with that is, you see on the lower left there, TELUS is the module that takes in the 3D ground model and collates all of that data for each individual specific location. So we have geotech data for every point, and we have water depth data for every single point. And we're able to gather that by taking the borings and CPTs at, say, 10 or 15% of the locations and translating that data to the balance of the locations through the geophysical analysis that tells us where the soil depths are. And you can kind of, the idea of the picture there is it shows you the different soil levels and what's in there. So that's the ground piece. Then there's the wind and wave piece, where we've got various modules that will bring all of those loads into the picture. And then we put all that together. And when we're doing the actual design using a specific turbine model, we're working hand in glove with the turbine OEM. They understand the aeroelastic performance of their turbine better than we possibly could because they've designed it, and each one of the manufacturers keeps all of that information as secret as they possibly can. So we have to get into an interactive load iteration process with the designer where we will initially come up with a rough foundation design, not using their loads initially. We give that to them. They come up with the loads, develop that, give us what the loads look like at the transition from the turbine to the substructure. We then take those loads, reevaluate the structure based on the loads back from the turbine manufacturer, repeat, and then you get to a point where you have a design that is tailor-made to the location and then able to be approved by a third-party verifier, which is part of the process in virtually every part of the world. There's a lot to this, fairly complicated, and happy to have questions asked. And if I get to the point where I'm making stuff up, I will absolutely pass that on to somebody who knows the real answers, and we'll be able to get back to you subsequently. So just some of the key design considerations here. You can see on the left-hand side there, there's a bit of a better picture of a monopile and a transition piece, giving you a sense of how these things interact. And that's just an actual design drawing with some of the sensitive bit blocked out in the middle for an actual monopile on a real project. So the parameters that we have to look at, we start with the ultimate limit state, which is the ultimate load that would actually cause the turbine to fail. And this is typically going to be the overturning moment at the mudline. The mudline is what we call the top surface of the seafloor where the monopile is penetrated. So in your extreme storm, you'll have significant forces pushing against that turbine. And if the forces are large enough and the resistance is weak enough, then you'll have the turbine pushing over to a degree that's unacceptable. You've exceeded your ultimate limit state, and you have to design to avoid that. And the ultimate limit state is a very important limit, particularly in areas where we're subject to tropical cyclones like the East Coast of the United States. Fatigue limit state is also a key parameter here. These structures are subject to constant loads coming from different directions in varying degrees. So you're taking this long, thin steel tube and bending it, twisting it, moving it around in all kinds of different directions for 25 or 30 years. So you have to design it so that the fatigue resistance of the steel is adequate for the fatigue that you expect the steel to be subject to. To do that, of course, you have to analyze all of your wind conditions and storm conditions to understand what you expect for fatigue. So we will build into this. We expect the 50-year storm to occur twice in the life of the project as the conservative analysis. We have to design to a fatigue limit factor of 3. So you're designing for 3 times the fatigue that you actually think it will see. And that's what drives a lot of the steel considerations. Natural frequency analysis is also a big deal. The turbine itself will have a natural frequency based on rotating components in the nacelle, the generator, the rotor, the wind turbine hub. And you have to stay away from that natural frequency throughout the rest of the structure. So if you think of this, it's a long, thin steel tube. So if you think of it as a guitar string, if you pluck the string of the guitar without holding anything down, you will get a relatively low tone. That's a low frequency. If you hold your finger on the fretboard and pluck the same string again, you'll get a higher tone. So the longer the structure, the lower the frequency, the smaller and shorter the structure, the higher the frequency, and it also will vary with the diameter. If you pick the thick string, you'll get a lower tone than if you pick the thin string. So we have to analyze diameter, length against the natural fatigue, the natural frequency of the overall structure, and make sure that we're not getting into any natural frequency resonance. If that isn't done right, then the entire structure will resonate. You may have seen the famous bridge that was doing this when it hit its natural frequency. That's, in engineering terms, that's a bad thing. So we have to avoid that and analyze the natural frequency. Accidental limit state is typically a ship impact. So there is the possibility that a vessel will strike the turbine foundation. We have to look at what the size of the vessel might be, how fast it might be transiting, et cetera, and examine what the impact would be and make sure that the turbine will be able, the structure will be able to survive that impact in a satisfactory state. And then the last of the limit states is the service limit state, which is really kind of closely related to the ultimate limit state. In the service limit state, you need to make sure that as the structure is subject to a certain number of storms, at each storm, you'll get some degree of liquefaction of the soil that's in immediate contact with the subsea structure. As that soil liquefies, the subsea structure will be able to move. When the storm passes, the soil will then resettle under the pressure of the water above it, and you want to make sure that the position in which the turbine resettles is within a certain range, typically 1/4 of a degree either direction. And that's your service limit state. Other key considerations of that limit states: erosion protection. This is seawater. Obviously, this is a very big deal. We deal with corrosion protection through a combination of passive corrosion protection with coatings, and we're using the most advanced coatings that exist for this sort of thing. Right now, it's epoxy glass fiber, and there's actually newer coatings that are being developed that we think will be able to outperform that. And we include with that active corrosion protection, either in the form of sacrificial anodes or compressed current systems, and put the two of them together, and that's what will allow you to achieve your design life. Secondary steel is really all of what we refer to as the secondary structures, meaning they're not carrying the main load of the wind turbine generator down into the seafloor. So these would be your boat landings and your ladders and your interior platforms and where the cable hang-offs are to pass the cables up, the equipment that sits on the platforms inside. Also a very important design consideration. And I'd already briefly mentioned the integrated load analysis, which we perform in conjunction with the turbine manufacturer. So as part of this, we develop, usually in concert with the turbine manufacturer, a design load case table. And this is actually driven right out of the IEC code that we use for the design of the turbines. And this is an extremely shortened one, just to give you a sense of the various design load cases that we would look at, whether it's producing power, whether it's in the park condition. That's often a very difficult one. And you see the I.1 and I.1 plung cases down there. Those are recently added to the IEC code as we've started to look at design, particularly in the East Coast of the United States, where we're dealing with our tropical cyclones, hurricanes. Prior to that, most of the design had been done for turbines that were going to be installed in Europe. And because of the trade winds, hurricanes simply don't go to Europe. So they were able to look at their sea conditions for a year, do a 50-year back analysis. That was going to be the most extreme storm that you would get, because everything would derive from that same storm source. And with tropical cyclones, they have a totally different derivation. So you have to look at that in a different way. And what we do basically is apply a robustness check to the design as it's going through its process near completion, subject it in the model to a hurricane, and make sure that it survives. And if it doesn't, then you have to go back and do some redesign. So just, we do this, right? Where we actually are turbine designers. Where some of the projects that we work on are located. And you can see that there's a huge cluster in Europe, which is where the vast majority of the wind turbines are. We're very active right now off the East Coast of the United States. We've been active in the APAC region now for a number of years. And we've started to do studies in both the West Coast of the U.S. and the Gulf of Mexico. Brazil is a potentially emerging market. The Mediterranean is coming along as a potentially emerging market. So offshore wind is being deployed across the globe, and we as designers go where the projects are. And this is just an overview of some of the things we do. I've actually, I think, mentioned most of these. We also do lifetime extension, subsea cable work, and other managerial project management, owner engineers type thing. Happy to talk in greater detail with that about that to anybody who's interested. With that, I thank you all very much and turn it back over to Craig.
All right. Well, thanks. Let's get our other presenters and panelists to turn their cameras back on as well. Matt, there's a bunch of questions in the background that have come in. If you can start answering those, we'll go back through in the order of things here to start our panel discussion. We'll actually start with Asia and then go to Kim and then over to you, Matt, to maybe choose one or two of the questions that you'll be answering on text and see if we can highlight that live. Now, a lot of our attendees for these webinars come from a surface water modeling background. And when we're looking at hydrology, hydraulics, we run into all sorts of problems when we take all the previous assumptions that we've made that, rainfall patterns and rainfall runoff relationships from the past are going to be used to determine, the frequency and the intensity of events going forward. So non-stationary is something we have to look at now for any large project or long-term water project. Otherwise, things get under-designed or over-designed. So, Asia, we were talking before a little bit about this. If we take that same approach to wind energy, if we take climate change and the patterns that are different, optimizing a location based on how things have behaved in the past may or may not be the right way to do it. You could in the future have maybe some unreliable power or maybe just dead air just sitting there. Any thoughts on climate change, just based on your background, climate change and how that might affect wind patterns, or even just some questions for the group? Hope you're muted.
Yeah, I'll try to answer that as best as possible. So with regard to climate change, there's a lot to consider. There are a lot of factors to consider, both the air and the water and the land. So, of course, with the increase in temperature and you have the El Niño Southern Oscillation cycles happening, there is change in the patterns where, there was I'm assuming a lot of these models are based on predictability over a period of time for the system to function, right? But, for example, in air, you have in my part of the world, we call them typhoons. So we have increasing frequency and intensity of typhoons. And so for Guam and the Mariana Islands, Typhoon Mawar just passed and the winds were 140 miles per hour with gusts up to 160. So, is it viable to put word from this perspective in Micronesia? Is this a suitable environment for wind turbines? Also, the hurricane patterns, you have Cyclone Alley, Hurricane Alley, Typhoon Alley. Sometimes this alley is either widening or it's shifting either north or south of where it has been historically recorded. So, things to consider. I'm a biologist I'm a professional volunteer as well. Also, when you look at it, how does it affect migration patterns of seabirds? How does it affect migration patterns of sea life? You also have the concern of structures providing vectors for invasive species. So if anyone is, familiar, the impact of fishing pressure on apex predators and the ecosystem impact of potentially introducing species that would not have a predator constraint, and then that risk from my perspective, where the baseline consideration before the turbines are installed, what does the baseline environment look like, and how might the installation affect that area? And so I apologize if I'm bouncing, but I'm going to bounce again. But this can also extend into commercial fisheries and even local fisheries scale. Even access to those fishing grounds may impact, because certain species, if these are for a community or an industry, they may spawn in one location or have a source in one location, and my internet connection is unstable.
No, it's breaking up a little bit, but I think that covers it pretty well.
All right,
If we can refer back to some of the questions that you've answered, thanks for answering those in the background. We will put the PDF files of the questions and answers up for attendees to refer to along with the recording. Kim, maybe let's follow up on that. Maybe if you could just offer a couple thoughts on climate change, and then maybe of all the questions you've been answering, thanks for being busy in the background there answering the questions, maybe just pick one that might be the most upvoted or the one that might be of the most interest to the group. And maybe just highlight that and recognize that everybody will be able to refer to your other answers on the additional resources that we'll provide. So first of all, your thoughts on climate change and how that affects what you do, and then any other questions you might want to hit before we turn it over to Matt.
Sure. Well, it's a bit of a circular discussion, right? We're doing this, we're talking about this, we're building these because of climate change. So it's kind of this, I'm not going to say vicious cycle, but there's the outer vortex, right, which is climate change at kind of the global scale and what we're trying to do with transferring over to renewable energy. And then you start honing in, bringing in the circle a little bit more to talk about, what are the physical impacts from climate change to what you're trying to engineer and construct? Are there any impacts from having it out there? So it's a little bit of this circuit. I'm not answering the question specifically so much as just pointing out that it's a little bit of a conundrum, right? So we can get ourselves kind of literally spun around the axis in terms of what are we trying to avoid? What are we also creating? But the really big picture, if we scale it out, is why we're doing this in the first place, why we're making this transition to renewable energy. In terms of a question to answer, Matt, I did kind of not punt them to you, but I gave my part of the answer and then said Matt be able to fill in a little bit more. I think maybe one of the ones we could talk about, because this is a big discussion in the industries, particularly in the U.S., is kind of this repurposing of oil and gas. Because if we are looking at truly a transition from one industry supplying our power and our fuel sources to this, then there needs to be a direct nexus, right? So we can't just say that is bad and this is good, and these are very independent. There is a Venn diagram. And so the question that came in though, Matt, was can we repurpose the oil and gas platforms? To my knowledge, that's not what we're trying to do, is actually, physically repurpose the platform themselves, because it's a very different dynamic structure to hold a tower on top and to operate in the wind environment and to do what it was physically designed to do. There's similarities, of course, but there is, I don't think you could just take the platform and stick a tower on it and call it a wind turbine. So, but with that, a lot of our discussion and maybe this is useful for some of the folks on the phone in terms of like supply chain and workforce development, and especially some of the students that might be listening right now, is that repurposing of knowledge and that transfer of knowledge from perhaps more of an oil and gas background to something like offshore wind. So truly the physicality, a structure in the marine environment that is doing something to generate electricity, those components are very similar. So there's a lot of knowledge transfer. There's a lot of, from a manufacturing perspective, that can be transferred. You're building these large components. So I'll stop there and let Matt speak for a little bit. But I do feel like there is a very natural, needed, worthwhile and meaningful transition from oil and gas industry into this offshore wind space.
Yeah, thanks. Yeah. Matt, before we hand it over to you, I'm just going to put real quick, since some people need to leave, we might run a few minutes over, but I'm going to put a few slides up here and just mention that any additional resources that we haven't been able to get to, I've got an extra website that I've set up here, hydroschool.org/marine, where we'll talk about marine structures. First, the structures being these offshore wind farm, wind energy projects. But we're going to have a series going forward of additional structures that we'll cover, and I'll continue to put some of those things here on this website. Now, while you're talking, Matt, I'm going to just run a few simulations here that the folks at Flow 3D and also JBA have provided to me, just showing some of the modeling that happens in the background for some types of structures that may have some relevance to offshore wind. Because there are a lot of modelers in the background here that attend these webinars. And I just wanted to show you some examples of some of the ways that we might model this with 3D CFD. Your 1D and 2D models are not going to handle this. But yeah, as you're talking and addressing those questions, I'm just going to run a bit of a slide reel in the background and show you a few of these things that are just going to play as we speak. So back over to you with the same question Kim had.
All right. Well, thank you, Greg. And let me just mention quickly, I forgot to include this in the prior presentation. A lot of the analysis that we do is in the time domain because you're looking at all of these environmental conditions, and wind and wave will misalign at different times. So it's a lot of time domain modeling, just like what you're showing right there. And it requires tremendous computer power. It's very, very CPU consuming. So for oil and gas, Kim is 100% correct. You cannot simply take an offshore oil and gas platform and plunk an offshore wind turbine on it. The oil and gas platform is designed essentially for a dead load, the weight of the equipment on the platform. So you're looking at your soil resistance in the vertical direction. An offshore wind turbine, it's doing this. So you're looking at your soil resistance in the horizontal direction. Totally different. And it's actually an area where we've had to do additional research because we simply didn't know enough about horizontal lateral loads going through soil. So it simply can't do that. There is tremendous similarity, however, most especially between offshore oil and gas structures and the offshore substations for an offshore wind project. The substations will almost always be jackets. There are some monopile substations, and that's being considered in certain locations, but you're limited with size. They're most commonly jackets. And in fact, the first offshore wind substation manufactured in the U.S. is being installed as we speak, or I think they've already finished, and it was built by Kiewit in Texas. So an existing yard that was able to build an offshore wind substation platform. And that's immediate repurposing. Even prior to that, the first 5 turbines that were installed in the U.S. were jacket structures off of Block Island, Rhode Island, and those were built by Gulf Island in Louisiana. One of the challenges that we'll face in transitioning from oil and gas to offshore wind is oil and gas is very much individual bespoke components. There's one of these, and it's really big. And there's another one of these that looks very different, except that it's also really big. And offshore wind, you're going to make 100 of almost exactly the same thing. And that's a very, very different sort of manufacturing process to manage. So it requires a lot more physical space. You want to do as much automation as you can. So there's a whole transition that will need to be made there. But there is tremendous knowledge that exists in offshore oil and gas that is directly applicable to offshore wind. One of the key ones being geotechnical and geophysical. In offshore oil and gas, you have to do those same types of surveys on a much more limited basis in terms of overall surface area you're looking at. but those same types of surveys to understand what the seafloor looks like underneath where your O&G platform is going to be. So we actually have quite a number of folks in our company who have transitioned from oil and gas to offshore wind, primarily in geotech, project management, some degree structures. Again, this would be people who would be primarily designing jackets for offshore oil and gas, now moving into designing jackets for offshore wind. So a lot of knowledge can be shared there, and really very important to tap into that so that as we do, as I fully believe we will, make the transition from fossil fuels to renewables, we take the people who are extremely talented and capable in the offshore wind business, offshore oil and gas business, making fossil fuels, supplying fossil fuels, and take those same skills and apply them to the renewable energy future.
Excellent. All right. Now, like I said, these are things that we have to compress into some fairly quick presentations just to fit the overall time frame, but we'll put additional resources up for you on the accompanying websites to go along with that. We'll also put a few things in the background then on some upcoming courses that the Australian Water School will be offering. We are the water school, but wind is a fluid. It behaves according to some of the same principles. Our nexus, though, is usually looking at how the wind affects the water, so not necessarily the wind itself, but we also want to look at the hydrostatic and hydrodynamic forces, how they affect structures. If you want to see more of this, if you want to see some courses in the coastal modeling regime, let us know. Next month, we're going to be bringing you some coastal content for our webinars. We also later this year will be talking about tidal energy, which has a lot of similarities there as well. So we look forward to your involvement in that. Let's go around and have everybody offer a couple of closing remarks then for the group. We certainly appreciate you coming on board. The people who come on board and bring you this content do so as volunteers, and we certainly appreciate your time. And on behalf of all the attendees, thanks for coming on with us. Let's go back again in the order. Asia, then Kim, then Matt. If you can just give us some closing remarks, your final thoughts on offshore wind.
Well, I take it from more of a natural resource perspective and biology perspective. I think such a conversation and collaboration among multiple fields to make sure that it receives maximum benefit. And I really enjoyed it, and I learned a lot. So thank you to everyone for my responses, and I'm looking forward to more.
Good. Appreciate your involvement, and thanks for answering those questions in the background. Over to you, Kim.
Great. Thank you. Thank you just for having me, for allowing me this opportunity to speak. Obviously, I'm very passionate about this topic. So I love having sharing that knowledge with others and getting people interested in it as well. So I appreciate the opportunity to share my knowledge and hopefully pique some interest. So thanks.
Yeah, and thanks for introducing us to Matt. Matt, bring it home for us.
Made a big mistake letting me go last time. As Kim knows, I'm delighted to be able to do this. Thank you very much. I really thoroughly enjoy doing these sorts of things and bringing the ideas and the concepts of offshore wind to what's largely a new audience. That speaks to the core of my heart. I've been doing this for 20 years off and on. This is really important. Renewable energy, there is no single solution. Somebody said once, it's not the silver bullet, it's the silver buckshot. And offshore wind is part of the silver buckshot. But it's one of the bigger pieces, to be perfectly honest. We can generate an awful lot of electricity using offshore wind. So this is a key area for us to explore. Very important, as Asia said, to tie together all the disparate aspects of it. We're actually looking at nature-friendly offshore wind substructure design. So there's many different areas of this to tie together, and lots more work to do over the coming years. So I invite everybody to get involved, to be part of the fun.
Yeah, watch this space. Certain politicians have decided that they're not big fans of wind energy. We'll stay out of that. But just because, everybody deserves a voice. And just because something is really cool, and I look at these things and these structures like, well, we can do this. This is really awesome stuff. Just because something's really cool and can be done doesn't mean that it should be done. we need to factor in decommissioning and things like that, and the environmental considerations. This all needs to be factored in. It's not, as Matt said, it's not the end all, not the magic bullet, but it is certainly something that can add to the overall needs that we have going forward, accounting for climate change and everything else that's going on. So in the background, you'll see a couple of extra courses coming up. Thanks again to our presenters. Thanks to the attendees coming on with this topic. Let us know what you want to hear more of. We look forward to being with you again. And on behalf of the Australian Water School, we'll see you next time.